Okay. So let me start where we stopped on Monday. At that point, I was finishing my class by describing the motor gestures that are associated with a particular behavior, which is songbird production. And I was showing you some results from our lab where a bird is monitored for its air sac pressure. As you remember, when these birds need to vocalize, what they do is they control the tension in these labia, and they control the airflow by increasing the pressure in some air sacs that they have. So if you monitor this air sac pressure as a function of time, you would have normal respiration, and from time to time you would have these patterns of pressure, and each time that the pressure is above a given threshold, then you're going to have the production of sound, okay? So what I'm showing you there in the first slide is the time trace of air sac pressure when the bird is producing this sound. And this is a canary song, and even if it looks kind of complex, if you look at each of these patterns, you will recognize something when you come from the field of nonlinear dynamics that is a family of periodic solutions from a very low dimensional dynamical system. So if anyone is interested in how you can guess what are the dynamical elements that you need in order to reproduce a time trace like this, I will be happy to discuss this with you, but this is not the issue that I want to discuss now. The idea is that you can have an ordinary differential equation which is two variables that are coupled nonlinearly, and you periodically force them, and then you can reproduce these time traces. From the physiology, these differential equations come from trying to describe the average activity of two populations of neurons. One is associated to a nucleus that is controlling the expiratory muscles, and the other one, the inspiratory muscles. So these are the two respiratory nuclei, are called RAM and PAM. And basically, at some point when the bird wants to sing, the telencephalon will take over and will generate this periodic forcing. So this dynamical structure is going to give rise, when you do this periodic forcing, to these different periodic solutions. And if you look at them, there is a huge similarity. The only thing you are controlling here is the frequency, and then the shape emerges from the nonlinear features of this system. As you remember from the first class, this is a bifurcation diagram of the two-dimensional dynamical system describing this. And in these different regions, what you have is different behavior. Here you have only one fixed point. Here you have only one fixed point. Here you have the coexistence of three fixed points. Here you have oscillations and so on. So the question I wanted to address today is how we can obtain low-dimensional dynamics from a large set of excitable units. We know that these nuclei, actually what they are huge ensembles of excitable systems. And we know that ultimately when they are driving these muscles, the dimensionality of the behavior is very low because you have basically periodic solutions. Okay? So the idea is that you have these hundreds of thousands of neurons, and then you took some average somehow, and you end up having a low-dimensional dynamical system. So how does it happen? So these are precise dynamical elements that you need in order to generate these time traces, and we want to recover them from an average theory of a population of excitable units. So how can you do this calculation? Can you do that calculation? Or do you have always to do numerical simulations? So the question I want to address in this hour is if you can go beyond doing some numerical simulations in order to try to reproduce the dynamics of an ordered parameter for the system. Again, there will be a simple solution, everything synchronized. But everything synchronized is an epileptic bird, right? So you have everything collectively going into low dimensionality. So the low dimensionality comes from the average, but the system has to keep its complexity. If you look at the experimental recording that I showed you the other day, have this calcium imaging describing how these units are turned on, and it's not a synchronic activity. So the average is something of low dimensionality, it's periodic gestures, but you have all this complex activity. So let me show you how these kind of calculations can be performed. So I'm going to start with a simple exercise, and I will go in detail in the spirit of this being a school. So if you're too bored, I'm going to be sorry, but you know, I wanted to show you an explicit calculation. So what I'm showing you here is a set of units which are coupled. And at the beginning, in my first exercise, they're going to be coupled all with each other. And I want to find another parameter describing the degree of synchrony of this, another parameter that would allow me to describe not only the synchrony, but also the average activity of this population. And I want to do it with a simple model for each of these units. So in order to do that, we'll go back to the example that I described in my first lecture, where we have this phase oscillator. The dynamics of this, each individual system is described by a phase. Okay? And we know that depending on whether omega is larger than 1 or not, you can have periodic solutions or not. So we know that if omega is smaller than 1, what we get is that the system is always increasing its phase, but if omega in absolute value is smaller than 1, what we're going to have are fixed points, one unstable and one stable, and the system behaves as excitable. So this is the simple dynamical system that I'm going to be using for describing the dynamics of each of these neurons. And I'm going to couple them all together, and I want to find what its average dynamics is. So a natural order parameter would be the total phasor of the system. So each of the phases will be associated to a phasor e to the I omega theta. And of course, if all these units are moving synchronically, all of them are moving synchronically, what you would have is that the order parameter that comes out of adding all these phasors is going to have a large amplitude. But then you can have all these units being active, but being out of phase. And therefore, when you add the total phasor for the system, what you're going to have is an order parameter that is very small in modulus. So keep this in mind, because what I want to have is a description where basically I'm going to have an average activity for this order parameter, which is small. That doesn't mean that all the neurons are in their equation state, but that they're out of phase. So the total system for this exercise is going to take many units, and I'm going to couple them with an impulsive coupling. So this coupling, what it means is the following. So it's not strictly a Coromoto model, for those of you that have been working with that. In the Coromoto model, what you are doing is you are coupling two oscillators. So you have one oscillator and another oscillator, which in principle will have different frequencies. But then when you couple them by the difference of the phases. This is a kind of coupling that is more pertinent for neuroscience, because the activation depends on the state of the other neurons and not the phase difference between the different neurons. So when one of these phasors is going through pi, then you are going to have a spike here because this term is 2. And if this is in its equation state of theta equal to 0, this is 0. Okay? So this is an impulsive coupling that is more or less reasonable for describing the impulsive coupling between neurons. We can do more realistic things, but for now, for this exercise, this is enough. So this is the order parameter, and we can write the equation for every one of the units in terms of this order parameter in this way. This is very simple. This is just a real part of adding all these phasors. So these are the equations for all the individual neurons. So in order to do the description of this collective state, what I'm going to do is to write the density distribution of these phasors. So I have here the phase space, and I'm going to claim that, of course, every one of these oscillators is going to be having, in principle, a different frequency, slightly different frequency, and I'm going to be describing the distribution of the frequencies, okay, for all of the oscillators by this density, G. So this is the distribution density of all the phasors. That means which is the number of units which have their frequency between omega and omega plus differential of omega, theta, and are in a position theta, between theta and theta plus differential of theta, etc. So this is the density distribution of all the phasors in here. And the only thing that I have, in order to start a description of this statistically, is the continuity equation for the density of the distributions. Okay, we know that the oscillators are somewhere. Okay, so they can be spiking and so on, but they're somewhere. So I have a continuity equation for the distribution F. And of course, I can start to work from here. This is a partial differential equation. The only thing that I can imagine doing is doing a modal decomposition and finding the differential equations for the amplitudes of the modes that allow you to describe the density distribution. So I compute it in terms of the order parameter, which is this term in here. Okay, remember that the order parameter is this. This is the continuous version of the order parameter. In the order parameter, when we were discrete, we were adding e to the I omega theta I. And now what I have is a continuous distribution. So the order parameter is just doing the integral of the distribution density times the phases. So this is a continuous version of the definition that I gave you before. And in terms of this, I can write the derivative of the phases, and I can plug it in here and trying to find the equations for the amplitudes of this distribution. So we start. We do the expansion of F, okay, doing a Fourier expansion. These are going to be the amplitudes of the mode, and I'm just doing a Fourier decomposition for the distribution density. And I have to plug into the continuity equation, okay, each of the terms, and therefore I take the expansion of F and I compute the partial derivative. What I'm going to have is a partial derivative for the amplitudes, and I'm going to plug this in here. Then I have to compute the product of the derivative and the derivative of the density with respect to theta. I do the little calculation. This is the derivative with respect to time, and this is the derivative with respect to theta, and I'm going to plug this in the second term. And then I have a third term, which is the distribution times the derivative with respect to theta of the derivative. I do the calculation. It doesn't matter. You can follow it. And the idea is to write the equations for all the modes. So we put them all together, and I do an expansion in terms of e to the I and theta, and the coefficient has to be 0. And that's the way in which you describe, you compute the amplitude equations for every one of the modes of the density distribution of the phasors in your phase space. Okay. Of course, we are in the same problem that we are always when we start from a partial differential equation. You do a modal expansion, and you end up with an infinite number of differential equations. So you are where you started, basically. No? You wanted to ask me something? No? So here is something very interesting, very interesting. Okay, and before we go, since we have an infinite number of modes, let me tell you something about this one mode, which is very interesting. If you look at the first mode, it plays a special role in this, because remember that the order parameter is to take the density distribution of the modes times the phasors and doing the integral. When you do that, and if you expand F in terms of modes, the only term that will survive is the first one, because the first one is multiplied by e to the I theta. That will cancel with e to the minus I theta, and it's the only one that will survive in the integration between 0 and 2 pi. So all this huge integral reduces to the integral between the distribution of the parameters, and the first mode. So the first mode is important because this one allows you to compute the order parameter. So if we know this mode and how it evolves, okay, we can compute this integral, and we will have the order parameter and the macroscopic description of the problem. So far, it's okay? Okay. Here comes the interesting thing. 10 years ago, Ott and Antonsen from the University of Maryland said, well, there is a huge class of problems for which the initial distribution, whatever shape you want to imagine, is going to be described in such a way that all these parameters lie in a manifold. You can write that the amplitude of all the modes are the amplitude of the first to the n. And then, this is the talent of Antonsen. How they got the intuition of that? Well, they said, look, if you take the derivative, what you will have is this equation, and all of them, you can factor out, all of them will be satisfied if this is satisfied. So that's the reason that led them to think that there was something special about this ansatz. And then they showed that that ansatz, that manifold, was stable, and it's a beautiful piece of mathematics that I included in one of the papers in the list, and whoever wants to study it, I will be more than happy to discuss it because it's one of the nicest papers in the last 10 years for me, for my taste. No? And anyways, so now we have an equation which describes one mode, and that mode enslaves all the other modes. Now, the order parameter was the integral of the first mode. And the distribution, let's make our life easier. Okay, we're going to, instead of using a Gaussian, let me use a Lorentzian. You will see why in a minute. Now, the issue is the following. Check this out. This order parameter is the integral of the first mode times this distribution. If you want to solve this integral, what you can do is go to the complex plane, like we used to do when we were in third-year physics or something like that, and you know that this integral can be done computing things between minus r, and then you complete it here, and actually the whole integral is just to take the value of the function in the poles, right? It's the Cauchy Theorem. So you take r going to infinity, you show that this integral goes to 0, and everything works fine. So this order parameter is just to evaluate the first mode in the pole of the distribution. And now the partial differential equation for the first mode, remember that we had a partial differential equation before, right? We had, for the first mode, a partial differential equation. But we know that if we evaluate this in the pole, you get an order parameter, an ordinary differential equation for the order parameter. Because you're evaluating alpha in one particular frequency. So now you have no longer a partial differential equation, you have a total differential equation. So this is a two-dimensional differential equation, complex. From there you can compute the first mode, and from the first mode, the distribution probability forever. So you have one initial distribution of probabilities for the phasors, and then you know how they all are going to evolve in time. From there, you can compute many other things, because if you do the calculation of, for example, which is the number of units which are spiking, what you have to integrate is with the distribution that you get, which is the number of particles that are going through pi, for example. And you have to integrate this, and this is a calculation that is simple to do. And now instead of having an order parameter that tells you how synchronous the system is behaving, you have a function that tells you which is the average activity of the nucleus, for example, which is a different thing. It's not the same to say that you have a nucleus where everything is spiking but out of synchrony than to say that you have a nucleus where all the neurons are dead. Okay? In one case, the order parameter is 0 because all the neurons are turned off, and in the other case, it's because all the units are out of synchrony. So phi here is a function that tells you the activity of the mass of the nucleus, the activity of the ensemble, and not the order parameter. But it can be computed as a function of the order parameter. So It's a very nice, intuitive macroscopic quantity. And like it happens in statistical mechanics in general, once that you have another parameter, you can compute whatever you want, basically. So I'm showing you just one calculation, the average activity of the nucleus, but you can compute many different things from the order parameter. What happens if you do it with two populations, excitatory and inhibitory? Well, the calculation, of course, is twice as boring, but basically it's the same thing. But the interesting aspect is that when you look at the bifurcation diagram of this dynamical system, now you recover all the elements that you needed in order to get the activity that I was looking for. So now I have a nucleus where I don't write a phenomenological equation for the activity, but I write an equation for all the phases. And I take the average, and this set of neurons behave dynamically with the same elements that I needed in my respiratory nucleus. So, yes?
Last class, you did this low-dimensional approach based in the gestures.
Right, exactly.
So you pictured this phase diagram,
right?
And now you deduce.
Exactly.
Following this
statistical mechanics
approach, and you find
the same, a very similar bifurcation diagram. Exactly. Before, what I was doing was I would take the gestures and I would say, I have a model which is phenomenological for the average activity of a nucleus. And I would say x dot is equal to minus x plus a sigmoidal rho plus cx plus dy. Y dot equal to minus y plus sigmoidal rho 2 plus ax plus fy. So this is the average description of a nucleus from a phenomenological point of view. This is an additive model, Wilson-Coe and this kind of models. Now, I find the bifurcation diagram, and it's all these things, and I find all these elements. And what I want to do is to know whether this phenomenological model can be actually derived doing some statistical mechanics from a bunch of phasors. And you get basically the same bifurcation diagram. Interesting thing is to realize that now I'm showing you a periodic solution of the average activity. But when you do the average activity and you get a periodic solution, you are not getting a synchronous activity of periodicity. It is much more subtle, okay? You are not having an epileptic attack where all the neurons are in phase. What you are having is a bunch of neurons that are in phase. So here I'm showing you the different neurons, and I'm displaying for each neuron, which will be aligning here with a point, the moment at which this phase goes through pi, okay? Now I have all these different neurons, and I color them with different codes, depending on whether they are repeating themselves once or twice or 3 times per each period of the average activity. So we can see which are the ones that are locked and unlocked and so on. And as you can see, you have a bunch of neurons which are really locked, and they contribute to this huge periodic spiking. But then you have other neurons that are in a period 2 with respect to this, and a bunch of neurons which are not in phase. But in average, they don't contribute to the periodic activity of the nucleus. So you have that the nucleus is not synchronous, but in average is displaying synchrony. So this periodic activity of the average doesn't mean that all the neurons are behaving periodically. You have a pretty regular dynamics, but the average is periodic. Okay. So, how do I test this? Because you have an experiment, you have a model, and then you did like 10% of the work. Now you have to use your model to do a prediction and do an experiment to validate or refute the model. So in this model, I have periodic, I have some periodic activity in a respiratory nuclei. It will be taken over by the telencephalon, which is going to be imposing some rhythm, and I want to find whether this model is good or bad. How can I test experimentally in my birds whether this model makes sense or not? So there is this colleague of mine who said, well, if you cool the brain, you're going to be slowing down one of the time scales of the problem, which is the telencephalic scale. And you're going to have that your song becomes slower. And I found this idea very exciting because in my problem, my patterns come out of forcing periodically this nucleus. And the different patterns were different subharmonics under the different frequencies of the forcing. So if it is true that I can change the frequency of the forcing, then I can change the respiratory patterns in a way which I can prescribe. So let me show you more precisely the theory behind this experiment. All these different patterns that I'm showing you here, the ones above are the experimental patterns, and the ones below are the theoretical patterns, where I take these low-dimensional models and I force them periodically, okay? And here what I have is, as a function of the amplitude and the frequency, regions with different colors that correspond to different shapes. So for example, here I have the green patterns, which are the period 1 solutions, and here I have the period 2 solutions, and here I have this other flavor of period 1 solutions. So this is what the model indicates. Now, supposedly, if I do the experiment and I cool down, I'm going to decrease the forcing frequency, and I should go from this pattern, for example, to this pattern in here. So A is the amplitude of the forcing, which I have no idea in my experiment. Is how active this telencephalon is. The forcing frequency is a timing, and this is another variable of the parameter in the model, which I don't want to talk about now. But the one that is pertinent is that cooling supposedly is moving in this direction. So with Matthias Goldin, a student in the lab, what we did is we built with small Peltiers these coolers. So you have to do a very simple surgery that is doing a couple of incisions in the cranius, and above the dura, you put some implants of gold. So here what you have is this Peltier. The Peltier, we built on top of it some plastic circulation patterns, so you can cool down the hot part of the Peltier. So one of the sides is cool, the other one gets warm, but you send water and you refresh it. So here it's more important the refreshing and the water than the electronics. No? And you have to do it very light because the birds don't like to have all this in their backpacks. So it takes a while to do this very light and in a way that is distributed in such a way that the bird doesn't suffer it and wants to sing, actually, after doing it. So this is the cooler.
At the same time, they heard the measure of the air sacs also?
At the same time, in some of the experiments, we measure also exactly.
It carry 2 backpacks.
It has to carry a big backpack. But at this point, the pressure transducer we get is much smaller.
Okay.
So there are technical tricks in here, but you're right. I mean, it's a complex experiment. You have to train them. When you want to do these experiments, let me make a little break from freaky experimental things. First thing is to do casting of animals. The casting is the most important aspect. It's like in life. You take the same experiment and you put it to a very aggressive bird, which is sexually very committed to all the females in the lab, and you know that whatever you do to this guy, he will sing. And basically that's it. So it's not also your talent, but your talent in knowing the animals. And there are other animals that you know that are not very competitive, and you can put them nothing, just look at them very strongly and they won't sing. So the casting is very important. So there are animals which are very aggressive, and for them, these experiments work. And then we did something interesting, that is, we built these coolers with a little hole in here so we could measure the electrophysiology of the neurons at the same time. So we could monitor for these birds the pressure, we could control the temperature, and we control the neural activity at the same time. This was a kind of challenge. So let me show you the kind of results that we get. So here is what the model predicts. You start, for example, for pattern B here, where the solutions are these small solutions in here. Here is the forcing, which we are not measuring. And then we know that if we cool down, we have to go to the green region where you go to period 2 solutions. And here we show below what the experiment gives you. This is the pressure pattern when the bird is singing, and then you cool it, and the pattern evolves into this specific shape. And the same story repeats for the different examples. This is a very interesting one. You are in C here, but in this region, when you cool down, you go to a period 2 that is first mounted on the period 1, okay, and eventually with the transient that is a large period 1. And here, when you cool down the brain, you get exactly the same pattern. So it's very precise for being something that is controlling the temperature in the brain of a bird. In the complete song, it looks like this. You take a song, this is a canary singing, and then you start to cool down. -6 degrees, -6.6, -7, -7.5. And basically these large patterns in here start to break in a way that is the way that we predicted. Let me see if I... Okay, this is... I will play you the songs in a minute. This is the result of the electrophysiology that you do simultaneously. This is the normal temperature, and this is what you see when the spiking takes place after you cool. So you do the cooling, and you get all this largening, okay, of the spike. So it goes slower. It is true. This idea that they had is true. You cool, and you go slow. I think it's very interesting. Okay, so... Yeah, this is an extracellular recording. Yeah. So what you do is you try to get into a region with a very high impedance. So these electrodes are very high impedance, so you get one neuron. And you have to look for it very carefully, and you have to look for the neuron. You have to be very close, and you are going to get only one spike. Yeah. So this is now, with the average model, taking into account all the nuclei of the bird. So here you see different colors and different arrows. They correspond to what we call different pathway. In the bird, the interesting is, people say, well, why do you study birds? Because you say, well, I'm studying birds, and people smile, the little birds and so on. But the reason you study birds is first that you have something that is very interesting, that is learning of vocal behavior, but the brain structures are very well separated. In a human, for example, we have vocal instructions that we learn. First of all, we won't do this kind of experiments in a human, but second, they're all mixed together. Okay, we have a brain which is highly integrated, but in the birds, you have the auditory pathway, which is a set of nuclei, and then you have the motor pathway with a set of nuclei, and if you lesion those, the bird will do everything as perfect, but only something will be diminished. So if you measure the activity in this particular nuclei, you know that you are affecting some specific aspect of their vocal production. So here in blue, you have the song system. It is a circular structure where you have the telencephalon, then it goes to RA, then it goes to respiratory, and to the nucleus that projects to the syringeal muscles, and then you have UVA, and you go back to HVC, and in HVC, you integrate the auditory pathway with the motor pathway, because they have to coexist, because the bird sings and listens at the same time. So there's a region in the brain where the two things coexist, and they have talked to each other in the same language. So it has this convoluted structure. And here what I'm doing is a model for these different nuclei using the bifurcation diagrams I had before. So in order to reproduce each of the shapes that I know are present in the experiment, for example, this guy is this guy is this one, no, sorry, this guy is this one is this one, and so on. When you do the integration, you know what you have to measure in here, and you know that here is something that has to be controlled by the temperature. The rest, I don't know because I don't measure it, but the model tells me what is the average activity of the different nuclei. So if I go with the model and I say, okay, I reproduce one of these patterns, what would happen if I make HVC slower? So I make this forcing slower at the level of the telencephalon. What should I expect at the level of the air sac pressure? So I change the parameters in the model, I make this wider, and what I say is, well, there is a specific signature, that is that this bump in here has to go deeper. So this is the kind of predictions that I say, well, I have something very precise that I can predict. If I cool in these large patterns, this minimum has to get progressively deeper, and the song has to break in parts. So the long syllables will have to become smaller syllables, for example. So it's the kind of predictions that you cannot do if you don't do the modeling, right? So here is an example of these pressure patterns when it's sung at different temperatures. And what you can see is that this long pressure pattern starts to get this bump, and it gets deeper and deeper and deeper, and eventually you break it into pieces, okay? So how does it sound? Okay, so I'm going to be playing you the same song, but when I'm cooling down, okay, with a current in the Peltier. Okay, you see, so the long one at the end starts to break into little pieces, and then you break it completely. Okay, and then you start to go the other way, and the bird starts to sing again the right song. 10 degrees, from 10 degrees. The maximum is 10 degrees, yeah. 10 or 8 degrees, something like that. Okay, and this is a phenomenological experiment that you do. But you have these descriptions of the model that tell you exactly what the different nuclei had to do for every particular neuron. So now, the next experiment. Go and put electrodes in these regions and try to see if in HVC what you have is the kind of activity that you predicted in your model. So this is just to compare the typical size of an electrode, and the darker regions here correspond to neurons, okay? And depending on the impedance, of course, you will get just a few neurons or several neurons. So typically you work with, I don't know, 100 megohms, and you get just a few neurons. The lower the impedance, the easier it is to get the signal, but more neurons you measure simultaneously. The higher the impedance, you measure just a few neurons, but you have to be really close in order to get them. So we used to build these little motors in order to put the electrodes exactly where we need it, but that's additional weight, so it's a problem. So there is a compromise, right? So here it's a recording where we have a bird singing, and we have the neural activity simultaneously recorded. And this probably doesn't mean anything to you, but to me it means a lot, because these syllables here, they are the long syllables that correspond to these long pressure patterns that I was showing you before, these very long ones. Okay, in the bird, when you have these long whistles, and the prediction is that the activity is right at the beginning. And you have the activity right at the beginning. And here you have simultaneous measurement in the left side, and you have the activity just at the beginning. This is an interesting aspect because there was a huge discussion in the literature on whether you would have sort of like a clock model that is a continuous representation in the telencephalon, or you would have these specific time instances that is what our model is predicting. And actually, when you measure that the activity is right where we are predicting it. And then you have these huge peaks of activity in the transitions that is a prediction of the model and so on. So this allows you to validate this model. So in other words, my claim is that the brain is very complex. And I agree that the brain is in a state where you have to move a lot, but it has to have the capacity to go to low-dimensional regimes in order to generate motor gestures which allow the animal to survive. Walk, sing, whatever activity it is. In those regimes, it is possible to do average computation of the activity of these out-of-equilibrium units. And what I've shown you is a path. It's not complete. It gets more complicated when the topology of the connectivity is different. But in principle, you can do these calculations, and you can get phenomenological models that are reasonably good. I thought I had a lot of material for the first hour, and I don't. So I'm hoping that you're going to be having a lot of questions, because in my next lecture, what I'm going to be doing is using this kind of knowledge in order to try to listen to what the birds are dreaming. But this is a completely different story. So I would prefer to stop here and use the time for questions.
So you have a model for collective behavior.
Espera, usar el micrófono así.
I think I missed something about the. You have a model for collective behavior for this burst of synchronized activity of sorts, but then you're measuring. You said you chose high impedance in order to focus on single neurons. Is that it? Why are you interested in few neurons if you have a model for collective behavior?
Okay. So in the case where I put this high impedance electrode in the middle of the cooler, is because I wanted to test the hypothesis that really what happens when you cool down is that the time scale of the forcing gets lower. And therefore, I wanted to have the particular shape of one neuron, and I wanted to see how it's stretched. So that is one of the reasons for which I am interested in that. The other one is because in this particular field, there is this very sour discussion on whether in the telencephalon you have a continuous representation of time or you have preferential spiking in some particular instances. So I wanted to show that that really you have synchronous effect at these particular events, and therefore I was interested in that problem. But if it's for me, neuroscience at this point should be more concerned with macroscopic measurements and do the thermodynamics of the problem first, and not the single particle theory. There is a big discussion in neuroscience of what is the level of description that you have to do. And many experimental neuroscientists are very focused on single unit measurements. That is beautiful, but then you have 10 to the 23 units, and you have to go to behavior. And we don't have the equivalent of thermodynamics. That is basically what you're doing, right? You don't have the thermodynamics of the brain. So my impression is that you have to do the thermodynamics of the brain first, and then, knowing that the basic unit is the neuron, try to do a detailed calculation. So, but in this particular case, it's because I have this fight, in the field, and I have to show exactly where the neurons are spiking. Yeah.
Maybe my question is about not like seeing birth, but when you cool down like 10 degrees below zero, the brain of the bird, was there any behavior in spontaneous activity in the brain?
Yes, there is less activity in the spontaneous. For example, we have a work on that, but I'm not showing it. But typically what you have is that the spontaneous activity is less frequent. If you
Any other behavior, like distress signals in the brain?
No, not that we measured. Not at this level of cooling. So it's only that. If you remember in the first class, we were listening to this activity when the bird was quiet and there is a continuous. Okay, so what you have is something which is rougher because you're having less units, but that's the only thing you find. More questions? We have a lot of time. Yes.
How difficult is to deduce equation for another parameter for another model, not a Coromoto-like, for instance?
So
is this possible? I don't know.
Okay, to go in this case, let's see. Okay. So the Coromoto model, one of the things that people doing Coromoto usually have is that the coupling is through the phase differences, and that is something that you can overcome and work models like this. We have gone beyond this by doing some models where you couple through a synaptic activity that is a solution of a second-order differential equation, and therefore it can have a delay with respect to the spiking. So you would have a spiking, and the current would have a delay. So we would do it with a coupling that is not impulsive and is not a cosine function or a sine function, but is the solution of a second-order differential equation which is driven by those. In there, what I use is a trick, that is that you can reproduce this shape as a solution of a linear model, because you know that in synaptic currents, you have that the shape typically is this, and this is the solution of a system which is forced by an exponential. And therefore, you can have a linear system which is kicked. Its solution is going to be an exponential, and that can be the kick of the second equation, and you can have a very realistic synaptic current. But the idea is that then, in that case, the equations are still linear. So you can do an average theory of something that behaves as a nonlinear system using that the equations are strictly linear. So you can go beyond this kind of coupling and do something that is more realistic, but you have to do ingeniously for each problem. That is my opinion. Now, concerning this, to have that this is written in terms of a sine-like function or a cosine-like function helps a lot. Helps a lot because when you have a cosine and you can express it as exponentials of the phases, then your life is easier. But it doesn't have to be something that is oscillatory. You can do the same dynamics by working with a kind of collection of sine functions representing, for example, by stable regimes and so on, and you can do calculations for things that are not excitable or oscillatory, but also be stable. So there is a possibility of extending it, but in my opinion, it's still work in progress.
Okay.
So I don't know how to generalize it in a big theory.
Okay, thank you. I have another question.
Thank you.
You're welcome. You assume that these neurons are fully connected to each other.
Okay.
So,
Perfect. Exactly.
So how it changes if you relax?
So basically what happens is the following. When you want to have a topology of connectivity which is more sparse, basically what you do is you order all the units in terms of how many connections are going to the unit and how many connections are going out of the unit. And within the class that has the same degrees of things going in and things going out, you can do this analysis. So you're going to have an order parameter for each subpopulation which has a different degree of connectivity. Therefore, depending on how complex your network is, the dimensionality of the dynamical system starts to increase.
Okay, and they're all coupled because...
Exactly. So even if they're all coupled, you can say, well, how many neurons are neurons that receive K couplings, K information from K units and go to J different units. And you can do the mathematics for each of these subpopulations. So whenever you have a small number of degrees of populations, you're going to have a small number of order parameters. But the more complex the network is, it is the higher the dimensionality of the system because you have more order parameters.
Yes, but you cannot uncouple the equation making some answer about correlation between an uncorrelated network or something like that?
That would be great. I have never tried it.
Okay.
So I don't know how it would work. It sounds like a very nice idea, but I have never done it.
Because I have seen it in the Butter model on complex. So
yeah.
Maybe.
Maybe it sounds very interesting. Yeah, super interesting.
Thank you.
Some other question? You won't be able to go to the coffee break at least until we get one more question. You want coffee?
No, one question. Since we're going in that direction that Pablo suggested, to more and more difficult stuff, can we do, I wonder if you could do plasticity as well? like a toy model, like
Yeah. Well, that's
K with K dot.
That's right. So again, if so, what Mauro is asking about is about plasticity. So what would be the regime to which you would converge if the coupling between these units evolves in time? So you would have to put an equation for K. So one of the most conventional ways in which you can do it is you can say that the K's basically are going to have some forgetting factors, and then are going to have something like a driven term that depends on the cosine of the phases between the two neurons that you are connecting. Why? That's right. That's right. The K12, for example. That's right. Because in that case, you would have that there is a strengthening of everything that is in phase. Okay, so if you're in phase, you're going to have a large term in here, and therefore you're going to be increasing K, for example. So you can introduce plasticity by putting some kind of equations like that and work your way through this calculation. I have never done it, but it's very interesting. But there is a guy who will come to StatPhys next week, which is called Mindlin, who did this very simple exercise, which is precise in this direction. He did it some years ago, but for example, he got this. He said, well, if you have two neurons which are coupled in terms of their phase differences, so you have θ1 equal to this, θ2, and then you couple them diffusively, then the K is going to be something like this. He then took the difference between these two variables, and he got the difference of this, whatever. So you will have a sine of θ1 minus θ2, something like this. And he got a dynamical system for the phase difference and the size of the coupling. And there is a beautiful dynamics where sometimes you converge to something and you learn something. You go to a fixed point in this phase space, which has the variables, the phase difference, and the strength of the coupling. But sometimes you get a periodic solution. So the system never learns. And it depends on the time scales of the problem, whether you can learn or not. Only two neurons. And synaptics don't converge to something, but they become irregular, and they alternate in time.
Someone must have done for a Coromoto model for them.
Eh?
Someone must have done for a Coromoto model, no?
I have never seen it.
No.
I have never seen it. I thought it was so charming. It was beautiful, but I never seen the continuation of this. Yeah, and for this system either. And it's very interesting what you can learn or not. Yeah, I think it's open. Okay, so if there are no more questions, let's take a longer break, and we continue. Yeah, and we continue for the last lecture. Before going to the break, here you have the time schedules for the presentations. Why don't you guys decide when you want to present? So come here, fill this where you feel comfortable with your presentation, and then we use this as a schedule, okay? Don't run for this. Okay? Don't kill yourself for this. Okay.
Sí, yo también.
¿Sí? Dale.
Porque empecé a copiar, pero no llegaba. Entonces,
Ok.
quería verlo. Está bueno, me gusta la perspectiva.
Sí, son lindas cuentas. La verdad que son lindas cuentas. Son lindas cuentas.
Just put your name, not the name of the paper, because this